Right. So we made the case before that we've talked about these two very discrete entities. One is how fluid travels in the subsurface as a free phase. It matters whether it's a D napple or an L napple. And we think that we can, based on knowing which one of those it is and some features of the porous medium that's going into, say something about the saturation distribution as a free phase. So that provides a source. It's stuck there. It's held by capillary forces. It's destabilized, if you like, or it's tried to be moved by gravity, but gravity isn't changing. Capillary forces aren't changing, and therefore it probably doesn't go anywhere unless things like rising and falling water tables are able to smear it around anyway, where it acts as a source. If it acts as a source, then this concept that we've talked about now of both diffusion and mechanical mixing, which act together, and advection, which also, in addition to mechanical mixing, carries it from one location to another, are the important features that represent the transport in the subsurface. And so that's what we've talked about last time, and hopefully you have some appreciation of exactly physically what that means. And so I think the end result of what we came up with last time, if we recapped, would be that we have we're trying to define behavior in some useful way. We have what we referred to as this advection-dispersion equation. I don't know that we have to belabor what it looks like, but we might as well write it out because we just have talked about what the individual terms might be. We have an accumulation term. We have a term that acts on concentration to say how it spreads out as we flow longitudinally. We have a term that represents how it spreads out in the transverse mode as we go downstream, if you like, from a plume. And we have an effect which is to advect it downstream. And so each of these terms, this is advection by definition. These are longitudinal and transverse. Let's see, both of them are dispersions. And this, I guess we said this is this other term. This is a minus. Advection, transverse, longitudinal, dispersion. If my handwriting is poor, which it almost certainly is, and accumulation. So what? So we have that. So what does that mean? Well, it means that if we, for instance, have in plan view this source area, then you can imagine that either at different times, this will be the extent of the front of the plume. Early time to later times, it'll get further. Or you could think of these as contours of concentration. The one at the outside will be the smallest. The one at the inside will be the highest. And in terms of our coordinate system that we've kind of alluded to, this would be the x direction. This would be the y direction. This would be also the longitudinal direction, and this would be the transverse direction. So in keeping with these subscripts. And so it's physically a way of being able to represent what goes on in these systems. And our interest is, if we know, for instance, what this source region looks like, And we know something about the advective velocity in the x direction. Of course, the advective velocity in the y direction will be 0, because we choose our coordinate system not based on anything other than the direction. We align it in the direction of the maximum advective velocity. And if there's a maximum velocity in this direction, like a car, the velocity of the car perpendicular to the car is 0, because it's orthogonal. There's no component there. And so we typically write the equations aligned along that maximum direction of maximum velocity. And so that's a curiosity in terms of what this represents. If we wanted to look at, say, a simplified system where, well, before we move away, what else should we say? We should say something about these. This is most definitely the advective velocity. This dispersion coefficient is equal to 2 components, right? We said that it's equal to one component which is equal to a coefficient of longitudinal dispersivity multiplied through by the advective velocity in the x direction, and it's plus an amount of diffusion. So 2 terms. So one term represents mechanical mixing. The other term, if you like, this one represents just the spreading of a ink drop in a beaker. I don't want to belabor the point. This is this. And if you like, this term here is, oh, we've drawn it before, as this idea that mechanical mixing occurs. And so if you start off with a distribution of a concentration which is upstream, by the time you look at that behavior downstream, it's spread out. And if you look at it along the length of the flow, yes, this would kind of be y. Maybe we should use y for that. Then this would look something like this, right? So this is, you start off with a drop of ink, it gets mixed as it goes downstream. It's physically being carried downstream by the advective velocity of the water. And because the particles diverge as they move downstream for the 3 mechanisms that we talked about last time, then it spreads out in this Gaussian distribution. And we made the point that this mechanical mixing looks identical to diffusive transfer by fixed law, and because they look the same, they all get lumped together in the same term, which is acted on by this second order differential. There's also a magnitude of this, which would be representing not the longitudinal dispersion, but I guess we could write it out also. It's actually worthwhile writing out. So the longitudinal component would be equal to, sorry, wrong, right? Transverse component would be equal to a coefficient that represents this behavior, but the advective velocity in the x direction, just like this one. Has to be the advective velocity in the x direction, not the y direction, because it's 0. And we want to index it here with some mechanism that's causing the spreading. And we'd add to this also this diffusion effect on it. So that in a physical sense is what's going on. Don't need to solve the differential equations, not the point of this class. Do need to understand what physically this might mean. And physically what it might mean is if we think about this behavior as being along an aquifer, and this aquifer could just be a core, an aquifer idealized as a core, then what we're typically thinking of is that at the upstream side we have some boundary conditions. And the boundary conditions are, if we think about them in terms of a concentration changing with time, then what we're going to do is we're going to just turn it on at some time. This would be T0, I guess. And all of a sudden, we turn on the upstream concentration. There's already fluid going through here at some advective velocity. This is in the x direction. What else was I going to write something? Oh, it has some length, I suppose. Uppercase L. And if we drew a snapshot at any particular time of what the concentration looks like along the length of this specimen, and if we take this value here to be C0, and typically we will just normalize the actual concentration we have relative to C0, so that would be 1 and 0. Then at some snapshot in time, we'd expect to have something that looks like this, if it's plug flow, where this distance here, this x would be equal to what? Velocity is equal to length over time. So length would be just the product of advective velocity in the x direction multiplied by the time that's elapsed. Nothing more than that. And the other thing that we're interested in is knowing, as you did for Longstreet, the assignments you're doing for Yucca Mountain, is what the residence time distribution curve would look like. Again, if it's concentration over initial concentration, this is just between 0 and 1. This is time. And if this were the case, then this would be T is, let's say, approximately equal to, because it's actually not true all the time. Again, it would just be equal to this. This would be, just rearranging this, this would be, this is the same as writing T is equal to x over velocity. If x is actually equal to the length, which it would be by the time it gets to this point here, then this is going to be just equal to advective velocity over length. And so that's what we'd expect. So don't need any differential equations to do that. This actually, that's actually, surprisingly enough, a difficult PDE to solve. So to get this solution that has this step front here and this step increase in concentration, which means that all of a sudden you're pumping water out at the end, and then all of a sudden you're pumping water that has this 100% loading on it. This is where the dispersion, in this case we only really have one component, right? Because there's only a longitudinal part. The transverse part is, it repeats itself, so there is no part, so this part would basically be 0. We'd ignore this. So this, if this parameter is 0, then it's just this first order differential equation. It's actually quite difficult to solve. It's very unstable, doesn't matter. But it's a very simple result. It's basically this result that you have here. If you add increasing amounts of dispersion to it, then what you expect to get would be that as you increase dispersion, you get this occurring, and in space you would get this occurring, where this is basically, it's not actually true, but let's take it as on trust for now because it makes life a bit easy. This is 50%. This is could be referred to as the center of mass, kind of, the arrival of the middle concentration. And this just represents the fact that, so this is, so the case for this being 0 is this, and the case for this being not equal to 0 or greater than 0 is this. And likewise for this. This is dl equals 0. This is dl not equal to 0, greater than 0. And so that's convenient because we could now, if we think this is one of the ordinates we have, this is 50% concentration and we have this time, then we can kind of draw this, except we don't really know how much this canters over as we increase the magnitude of dispersion. And we explained this last time that physically what that's really representing is that if you think of the behavior around this front, what this would physically look like is that you have some pathways through here that's able to go through, and so the front of this pulse has gone down the fast pathways, and everything that's red behind here is contaminated at 100%, so the relative concentration is 1. But if you look now at drawing a section across this point here, part of it would be red, part of it would be white, and so it would be, on average, it's 50%. Further ahead, there's more white than red, and so it would be less than 50%. Behind it, it's more than 50%. So physically, you just need to get an appreciation of what's going on. And so that's what we'd like to be able to do. Presumably, we'd like to be able to say exactly what this distribution of concentrations might be along here, because if you're pumping to remove water along here, you control the velocity at which you move it, and therefore you might like to come up with some predictions of more accurately what this concentration distribution might be. You might like to have a more accurate indication of what the arrival time would be, because actually if the dispersion is 0, you get this sharp front here. If the dispersion is slightly larger than 0, it's like this. It turns out that if the dispersion is really large, then you'll also get cases where it's like this. And so it arrives quite late, because the velocity in this case would necessarily be small, but we'd like to know this case because it's not really predicted by that. So in some cases, that's why I say be careful of always saying that the 50% mark acts at this point, because it doesn't. And we'll see that in a second, right? So what we might like to do is come up with some ability to be able to predict what's going on. And so this actually isn't any different from what we talked about last time in terms of, I think we drew some pictures, these pictures, basically these pictures. These would be the upstream concentrations that we talked about for the reservoir. This is what it looks like along the core. And we didn't draw the downstream portion, which is the right-hand side on the other part. We can do it either for a step change in concentration, which is usually what it is. If you have DNAPLs sitting in the pore space in this kind of chimney, they dissolve so slowly that they basically act as a constant source, replenishing whatever is moved. And less like a spike that then removes itself in time. And so we'll concentrate on the former behavior rather than the latter. And so we can do some things in solving the differential equations to be able to say exactly what's going on. And we can use some standard results. We're not going to develop the equations ourselves. And the standard results just rely, these are in Fetter, so you can refer to them if you so wish. They take an aquifer which is idealized as a one-dimensional case. It is flowing in the x direction, could be inclined or whatever, it doesn't really matter, it's just along the length of it. There's some advective velocity occurring along the length of it. The length of the core to the point where you'd like to measure what the concentration is given by some length L, just as we drew it before. And we're going to change the upstream concentration to basically turn it on at some time t0, and it's equal to some upstream concentration. And what we'd like to be able to do is get a solution that represents that. And the solution that represents that is this. Just going to jump straight to it. Don't need to derive it. And so the solution is defined in terms of a couple of useful parameters. It's defined in terms of the properties that describe our geometry. And so we said that the properties are the length it has to flow, the advective velocity that it's flowing downstream at, which is this v sub x in this. So this. Any particular time we choose after we started this. So I guess time would be the time after we turn on the concentration. So length downstream, velocity of flow, the time after which we've turned the concentration on, and dispersion, defined as the magnitude which is equal to the two components that we talked about. A coefficient operating on the advective velocity and also the molecular diffusion part. And so these are the I guess 1, 2, 3, 4 properties that describe the behavior of the system. The other thing that we could do, don't know if it's worthwhile doing it, but it's pretty straightforward to do, is we could also take this expression and we could define it in terms of a couple of variables. And these variables are this one here. And if you remember back to looking at fluid mechanics, we always talked about making dimensionless properties. And there are two important dimensionless properties here. One is called the Peclet number. I think it's got an acute on the first E. Peclet number. And it's equal to a ratio, just in the same way that Reynolds number is a ratio of, inertial to viscous forces, right? That a Peclet number is the ratio of advective flux in other words, an advective velocity times the length divided by a diffusive flux. Which is proportional to this parameter d sub L. So it's just the ratio of two properties. So when it's bigger than 1, then it's dominated by advection, this transport downstream through the system. And when it's much less than 1, it's dominated by molecular diffusion. So much larger than 1 is flow in a gravel or a sand. Much smaller than 1 is flow in a clay barrier or something. So that's one important property, or non-dimensional property. The other one is TR, which is actually a pore volume. I guess 2 words rather than 1. Here it's called T sub R. And I suppose it is the volume injected upstream in the core relative to the pore volume. If you can read that. Can you read that? I can read it just, but maybe not the back. So pore volume is just the number, the volume that you inject relative to the total pore volume. So by definition, if you have a pore volume of 1 cubic meter in your system, you inject 1 cubic meter, then at that stage, the stuff that you've injected since you started injecting that amount is just ready to come out at the other end. And so 1 pore volume is kind of an interesting, or pore volume is an interesting property, because you'd think that if you look at these residence time distribution curves that we've talked about, in terms of, we defined this in terms of a time before, but you could also determine this in terms of, I guess, TR, which is a pore volume. And if that's the case, this is 1 pore volume. So this breakthrough, yep, shout. Gotcha.
What's that term in front of, like the L minus K T over the 2 square root? Yeah, right in front of that, what's that?
This is the complementary error function.
Okay.
Just a mathematical term.
Okay.
So we'll talk about it soon. Complementary. Yeah, good question. And as far as it's an integral of an exponential. But as far as we're concerned, it's just a standard result. It's that we'll use. I don't know if your calculators have it. Certainly, MATLABs and Mathematicas have it. This is exponential, so this is just e to the plus this term. This is just error function. Complementary refers to the c on it. There's also the error function, which is just the error function without the c, which is 1 minus it. Doesn't matter. But anyway, it's an exercise for you to do on your own. But what you can do is if you substitute into this expression just by multiplying through by L's and D's and V's, you can convert this expression to one that relies only on the parameters of Peclet number, which is an index of how fast flow is going relative to dispersion, pore volumes, a relative concentration, C over C0, and finally a characteristic length, which is X over L. So those are the 4 properties that describe this behavior. And so here this is that rearranged expression shown here. It defines a relative concentration as a function of Peclet number and pore volume, these two. And it just happens that it defines it only at one location, which is equal to X over L equals 1. So in other words, at the end of the tube, the end of the sample. And so if you do that, then you end up with a unique, if you like, diagram that gives you the breakthrough behavior of fluid coming out of the end of the sample, which is this, which is what we've said before. Maybe it's worthwhile blowing it up. In terms of these 4 parameters, it's a function of the number of pore volumes. It's a function of how big the Peclet number is. So instead of defining these curves as one where the dispersion is equal to 0, so in other words, if the Peclet number is equal to a velocity times the length over dl, we said before that this kind of instant breakthrough, this plug flow, was where the dispersion is equal to 0. Dispersion is equal to 0, then the Peclet number has to equal infinity. So this is for an infinite Peclet number. If the dispersion is no longer 0 but larger than 0, then it would behave something like this, where it would kind of go through this 50% point here, and it would occur at 1 pore volume. But if we keep on increasing the amount of dispersion, make it mix even more, then we find out that at some point it no longer goes through this 50% point here, 50% and 1 pore volume point. It actually arrives earlier and progressively earlier. And so these are the cases which would be, I guess, diffusion dominated or dispersion dominated. And so these are just, we can calculate these. And so I guess you don't really have to do the dimensional analysis, seeing as I couldn't do it today. But I don't know that you necessarily need to do these calculations either. They're relatively straightforward. If you use any expression like Mathematica or MATLAB, then you can put in this expression. So this is a half error function, Peclet number for TR. This must be an error function. Oops. Yeah, square root. Square root, Peclet number. Someone alive? Did we lose someone? So this is this expression here. Peclet number 4 times pore volumes, 1 minus pore volumes, etc. Exponential. And so what do you expect it to look like? That may be a first for me. Actually, what is this? Yeah, so this is it. So this is exactly that curve that we've looked at. It was in the background. So let's go. So this is pore volumes along the bottom. 1 pore volume here. If the Peclet number is very large, what was the Peclet number? Peclet number is 100. I guess that's big enough. Let's make it bigger. What would we expect to see for big Peclet number? Too big. Doesn't like it. Nothing to plot. Why is it doing that? What was it doing before? Why did it? Okay, it doesn't like it larger. So looks like it doesn't like to do 1,000. Never mind. More worried about. So this is kind of the plug flow behavior. This is one pore volume. If you go up here, this is roughly 50%. Did you go across here? If we use progressively larger dispersion magnitudes, then we'd expect that it's going to flatten out, right? It should flatten out. So now this one pore volume, that's roughly the same. Actually, it's a bit higher. Looks like it's about 55%. If we use 1, so by definition, the magnitude of 1 is where dispersion and advection are equal, whatever that means, the fluxes are equal. And you see there that this 50% mark is occurring now much earlier in terms of pore volumes. So this is the case. So when the Peclet number is large, it's a shock front that's moving through. You don't see anything ahead of it because it's water ahead of it, and then it's dissolved in water behind it. When it breaks through, that's the first time you see it. When you are going through at a much smaller velocity and therefore larger velocity and larger dispersion, then you have these fingers, which is this mixing. And so when the first of these fingers arrive, then it's kind of a dilute concentration, which would be at one pore volume. You'd end up with some magnitude coming through. I guess this isn't in space, this is actually in time. So as soon as it breaks through, actually at one pore volume, at 0.4 pore volumes, it's come through at a concentration of 40%. At 0.6 pore volumes, it's come through at 55% concentration. And so in other words, these fingers, the front really is only here. The tips of the fingers represent, literally the contaminant fingers are ahead of it. And so we've only come 40% in terms of pore volumes, but because of this dispersion ahead of the front, we actually end up having it break through at 0.6 of a pore volume instead of having to wait for 100% of a pore volume to be able to get it through at the full amount. And so it's a standard result that just allows us to be able to calculate that. And so it is useful for us to be able to do this in terms of these non-dimensional properties, because what we've basically said is that we can describe this behavior in terms of 4 variables. One is a relative concentration. One is the fact that we're measuring the concentration at some location downstream where the x-coordinate is equal to the length. So this is equal to 1 for all of these. And therefore, since it's completely controlled, the equation is completely defined in terms of these 4 variables, the other 2 variables fit very plainly on a 2-dimensional plot, which is this. And so we didn't talk about this last time. It was on the end of the last plot we talked about. But this is out of Fedder's book. And this is exactly the same plot that we've drawn, calculated. And so the left-hand side is relative concentration. The fixed step function that's noted here. So there's the 3 solutions here, the 3 solutions that are in these notes. Really the only important one for us is perhaps the one that we talked about, which is if you look at the upstream reservoir for this core, is that we turn the concentration on at some time 0, and we keep the relative concentration 1 from then on afterwards. Fixed step concentration. That's step, obviously. And so the results for this are as follows. These are pore volumes. So this is a TR equals 1. So this is when one complete volume of fluid is flushed through. This is for the highest Peclet number here is a Peclet number of 100. The solid line is this line here. And as you look here, if you go across, if I can draw this horizontally, then this basically should be, it's actually not quite 1, it's to the left of 1, slightly, only slightly. If you look at the others, then this is a Peclet number of 10. No, it isn't. This is a Peclet number of 10 here, this one. So this is Peclet number equal 10. So exactly as we expect, instead of being vertically, it's canted over, meaning that because of larger dispersion, even as you've only put through half a pore volume, you're getting some low concentrations coming out the other end. And the Peclet number of 100, sorry, it's the opposite. I can't do that. Peclet number of 1 is this one here. It goes off here. And so they're kind of shown in Cameo. I mean, I think they are physically shown in Cameo down here. This, right? Very large Peclet numbers, smaller Peclet numbers, even smaller numbers. But basically all they're doing is allowing us to be able to represent the behaviors if you wanted to define what the concentration distributions were downstream. And so if you wanted to be able to put together the concentration arrival map, the so-called residence time distribution, the RTD curve, versus time and concentration, then you have exactly that here to be able to do that. That's exactly what this is. And so where it comes from is just this calculation from these somewhat complicated functions, but not very difficult to calculate if you have something like a scientific calculator or MATLAB or whatever to be able to do that. And so the important thing is to realize that, I guess the one thing is that we cannot always take the fact that, as you've done in your calculations so far, that advective velocity is equal to length over time. That certainly is true, but we can't always use this to give us the time at which it arrives is going to be equal to the length traveled divided by advective velocity. Even in the average, right? It's true at this case, because at this case it's basically at 1 pore volume. But if you use this calculation, this is the arrival time of the plume downstream in terms of the 50%, say the 50% concentration amount. It's not going to be true even if the Peclet number, this is not true, I guess, if the Peclet number is less than 10. Just from this, right? This curve here is this one. Instead of being 1, it looks like it's 0.8. So it's not far off, but it's not really very close. If you look at Peclet number of 1, then it comes through at only 0.45 pore volumes. So I guess we're atoning for our sins, if you like. This is not a bad calculation in some ways when you want to calculate behaviors in strongly advective flows. But if it's diffusion only, and you're relying on an advective process to do the calculation of when it would arrive, it's perhaps not surprising that it's a bad estimation of that, because the processes by which it's being transported are not really controlled by advection at all. They're controlled by diffusion, and diffusion doesn't come into the estimate. So how could you calculate an arrival time if you're using a parameter that doesn't include the chief characteristic or feature that controls that transport? I guess that's really what we'd say, right? So you don't need to know how to be able to evaluate these expressions in what we'll do, but you need to be able to recognize that what residence time distributions would look like and where those might come from. We can do them from different boundary conditions. I'm not going to talk about that. The other one that would be relevant to us would be this Dirac delta function, where you just spike it. So in other words, this is the same as taking a mixture of DNAPL and water, DNAPL dissolved in water. So it's only aqueous phase, and you inject it into the ground at one time. There's no source region which is continuously replenishing it as a constant source, which is this step function, but just a spike which gets carried downstream. And the solution for that, again, in the same way that we talked about before, is given here. And you can go to Feta for that. The easier way, maybe, to think about this kind of source in the ground would be to think about injecting this not in the upstream portion of a core plug or a Darcy flow chamber or a diffusion chamber, but to think about dropping it into an aquifer and looking at it in plan view. And so the two solutions that I'd say are important are the one we just talked about, this one where we get these residence time distribution in terms of relative concentration and pore volumes and Peclet numbers, which we spent a bit of time talking about. And the other one, and that's for a step increase in concentration, really represents that you continue to dissolve stuff from upstream and it replenishes itself as it gets washed downstream. The opposite of that is this delta function where you inject something either into a core plug like this or perhaps more reasonably into an aquifer. And so if you're looking in plan view about that, say you inject some water into an aquifer, X and Y are the directions in the horizontal, Z is vertically. And at some time t0, you drop this in and you let it do what it's doing. It's a bit like a pebble being dropped into a pond. The water in the aquifer is carrying itself downstream. And so you can imagine that if you looked at this ripple from this pebble going downstream, it would spread out due to dispersion. So at time t1, it might look like this. At time t2, like this. Don't know why it's doing that. Time t3, it might look like this. Time t4, it might look like this, even bigger. And I'd guess that if you drew a cross-section across this, then you'd probably expect that this cross-section might look like something like this in terms of concentrations. This is C over C0. This would be the x direction. If you did a cross-section transverse to it rather than longitudinal, then you'd end up with something different. If you looked at it up here, then maybe it would look a little different in that it might look like this as opposed to this. So nothing different from what we've talked about before. And you can think of this as basically being a cloud. So this is, the puff of smoke that comes out of the chimney at some location upstream, and it disperses as it goes downstream. Just like in the atmosphere, most of the things that mix up clouds are actually mechanical dispersion. It's not flowing in porous media, and it's probably just mechanically dispersing more than it is diffusing. And so we can get an expression for this dispersion. And the expression for it is actually relatively straightforward. It's basically calculated by assuming that you take a coordinate system that you attach to the average velocity of a particle that's going from here downstream. So in a given length of time, the center of mass, really, of this material that you've put in here, the mass of which was this amount initially, it looks like it's more, but it's actually not more. It's more spread out and less tall. And so you can think that the area under this curve, which really represents this total mass, would be the same. Tall and skinny, really, really tall and skinny, but not so tall and quite broad. The length that it would have traveled downstream would be, this length here, which would also be the same as what we will call uppercase X. And the solution really is just the same as taking a beaker, dropping ink in the beaker, letting it disperse, and physically translating that beaker downstream at some velocity times time to give you a length traveled in a given time. And the solution that comes out of it is just the spreading of that, dispersive spreading of that ink dot within the system. And this is the expression for it. And much easier to plot. I haven't plotted it, but it's just the exponential. It's an exponential for a length relative to a coordinate system. So I guess actually this might not quite be true. The idea is that the coordinate system migrates with the cloud. And so at any given time, the concentration relative to that cloud is just given by the x, y, and z coordinate system, which are physically translated downstream. And so if you know what the advective velocity is, if you know how long it is since you introduced it, then you physically know where the origin would be relative to your point. And then now when you calculate the concentration distribution, it would be defined relative to this coordinate system, which instantaneously is at this point, but 10 minutes later will be further downstream at a different location. Right? So it's just centered on this point. And so you see these terms, a length squared, a dispersion, magnitude, and a time. It's an exponential of that, and so these terms should be non-dimensional. So this is length squared, this is length squared over time, times time. So these indeed have no dimensions. And instead of working in concentration, this is the amount of mass that's put into the system. If you like, the mass of solute. So in other words, milligrams or kilograms, it doesn't really matter. And again, that should be equivalent to some magnitude. This is non-dimensional. This is a concentration, so I guess this should be a mass per unit volume. So if you do the dimensions on this, I'm loath to do that after what I just did so badly this morning, or this afternoon already. It would be kilograms, right? This would be seconds to the 3/2. And this would be meters squared per second, which are what each of these are. There's 3 of them, so it's cubed, right? This, this, and this, 3 of them. And it's a square root, so it should be 2. So let's see if I can manage to do that. It's seconds to the 3/2 times seconds to the minus 3/2. So these cancel out. And it's meters squared, square root meters. So it's the units are kilograms, meters squared, meters cubed rather. So indeed, this is a concentration consistent with these other dimensions. I did manage to get that one out. And I guess the other result would be that if you look at the center of the plume would always be, if you draw it in plan view, I guess, the center of the plume would be these uppercase X's and these uppercases Y's. And if you draw it in terms of concentration, as we tried to draw it before, something doesn't make sense, is that you'd imagine that the maximum concentration indeed would be in the center, where if this is the value of the x coordinate, this by definition is 0. So if you put x and y and z equal to 0, this exponential I think becomes 1, and then for the concentration at the middle point, which would be the maximum one just by looking at it, is going to be this value here. So that's all this is. So it's kind of logical. Doesn't matter so much about understanding where the equations come from, but getting a feel for what they physically mean, I think, makes some sense. And so you could always get the maximum concentration as it transits downstream just from this expression. Kilograms, seconds, meters squared per second, etc. Yeah. and so on. And so a standard result that comes out of that, because really, if you think about it, this distribution that we have here is nothing other than the normal probabilities distribution, the so-called Gaussian distribution that we curve things on typically. And so the other characteristics, I guess, of that, which come into some use here, is if you think of this plan view of this cloud as it goes downstream, down gradient, downstream, and you look at drawing the cross-section through this, so in other words through here, which is what this is, then the definition, as you probably recall, of 3 standard deviations is the location that includes, I think it's written down there, right? So it's 90, it's this number here. So in other words, 99.7% of the mass of this plume is included within 3 standard deviations of the location of the mean. Physically spaced a length that's 3 standard deviations the spacing of the mean. And so that's kind of an interesting result for us, as we'll see, mainly because, for instance, if you could think about going into an aquifer, and at a particular time, if you could plot exactly what the concentration distribution was within that aquifer in terms of the periphery of the cloud, and you knew exactly what this length was here, that actually is 3 standard deviations, then the standard result is that 3 standard deviations multiplied by the cube root of 2 times the dispersion times time is a standard result. It's the standard result of this behavior. And so if you know that this length here, if you can physically measure this length in an aquifer, how big is the plume, then immediately you know this. If you know how long it is since it got dumped into the ground, sometimes not a very easy number to know, then you have this. And you have everything you need to be able to calculate the dispersion in the system. And so physically you could calculate the material properties of this dispersivity, which we've said before is something like this. Which is a physical property of the flow system. You could calculate exactly what this was by being able to measure the 3 axes of the ellipsoid. The length of it, this length here, the width of it, which would be this length here, and I guess the depth of it into the page, which would be the 3rd one, which are all these 3 things. And we'll do that as time goes on. And so it's not completely a worthless thing to do. Why do we want to do that, right? If you wanted to do that, you could get this. So what this would allow you to do is, if now you know what this dispersion coefficient is, and you think that nothing is changing in here, this parameter isn't changing, the velocity at which it's being advected isn't changing, and diffusion coefficient isn't changing, then it would tell you that in some extra time, the center of mass would be at this location, and it would be bigger. And it would be bigger by some other amount, because now at some new time, you could calculate what the new size would be, and you could also calculate just from velocity times time, is the length traveled, exactly where it would be. So perhaps a bit more, just almost time to go. Perhaps a bit more grounded in terms of physical intuition, I guess, in this case, is that you put this stuff into the aquifer, it travels downstream. In traveling downstream, it diffuses a little bit, it maybe disperses mechanically and mixes a lot as it goes in and out of the pore spaces, and spreads out as it goes downstream. So the cloud, as it goes downstream, gets larger and larger, and less concentration. And so physically, perhaps that is not so difficult to understand, but the characteristic dimensions of it as it goes downstream will change. As a function of time, it'll get larger, and it's controlled by the mechanical properties or the dispersive properties within the aquifer, which are useful to be able to predict from one realization where it is after 10 years, where it might be after 20 years, if you don't do anything. Yeah, that's as far as you want to go. And so that's exactly how we can use it. So we have an advection dispersion equation. We know that accumulation is equal to a mixing part and an advection part. We know kind of what each of those components are. We can break it up into two important physical properties: Peclet number, which relates the advective flux to the dispersive flux, and pore volumes when looking at the one-dimensional flows, and those make some sense, hopefully. And when we look at three-dimensional flows in an aquifer, we can look at it through, again, the similar concepts, where you look at just spreading around a center of mass as it goes downstream, and we can calculate some features of that in terms of the length of the cloud and the width of the cloud after some particular length of time that's been traveling. And if we know what those lengths are, we can use it to back calculate what the properties are. If we know what the properties are, then we can predict in the future where it might be and what it look like. And I suppose if we also, the other thing I guess you can do is if you know what it looks like at time t, and you're lucky enough to know exactly how much later than the initial spill it was, you should be able to calculate exactly what this origin would be as well, right? The initial point, just by back projecting, in theory. Not so easily done, but in theory. Okay, so that's it. All right, so we'll carry on with this next time to talk about how we might measure some of these things, using these expressions and other things. And then after that, we'll talk about conservative transport, where no longer is all the mass that goes in upstream ultimately delivered downstream, but some of it gets sorbed onto the material around it. So we'll talk about that next time.